Welcome back. Let's begin chapter 5, polar coordinates and equations, so polar geometry for short. So polar coordinates, first of all, let's just have a quick introduction. So Cartesian coordinates are simply your x and y. So this is a way of locating any point on a two-dimensional coordinate plane, so on a piece of paper. So as long as you've got the reference point, the origin, x tells you how many across you go, and y how many up or down. Another way of locating a point could be by giving the position of that point through two coordinates that are not x and y. So the first coordinate would be what we call r, and this is the length of that pink line, so the distance from the origin to the actual point. In fact, that origin, if you were to draw it on the polar grid, it will be referred to as the pole, and you wouldn't have x and y axis, you would only have the positive x-axis in that, so starting point at the pole and going towards right horizontally, it's called the initial line. So it's your positive x-axis is the only remaining line from the axes. Okay, the second value you give is theta. Theta is measured from the positive x-axis or from the initial line anti-clockwise. There you go. Okay, so let's just write a few definitions. What is r? So r is x squared plus y squared square rooted. Okay, so I use simple Pythagoras and you get your value of r. Theta is going to be your tan inverse or arc tan of y over x. There you go. And it's normally, well, it can be given in degrees, but most of the time it will be in radians. So they should accept either, really, but if they specify, then you need to use the units of measurement that they requested. Okay, so you need to be able to interchange between the two coordinates confidently. So the first section of the chapter is really for you to get used to carrying out that interchanging. So changing from polar coordinates to Cartesian and from the Cartesian to polar coordinates. So in this example, we've got three different points. These are Cartesian coordinates, so we are going to find the same positions in polar coordinates form. So always draw it. So 3 across, 4 up, somewhere here. There's my point over here. So for polar coordinates, I need to find what r is, and r is just x squared plus y squared square rooted, so that's going to give me 5. And here is the angle theta, so theta is going to be your tan inverse of opposite over adjacent, so 4/3. I'm going to reach for the calculator, just check that I'm in radians. So 0.927 to 3 significant figures, so putting it in brackets, 5 and 0.927 radians. Make sure that when you see two coordinates given in brackets, you read check whether they are coordinates given in polar form or Cartesian coordinates. So here we've got another point. This time is going to be 5 across 12 down. So this is 12, this is 5. We're talking about going over here. I'll find this angle, although I'll provide this angle as my theta. Okay, so first of all, let's go for value of r. This is 5 squared plus 12 squared, square rooted, so that's 169 square rooted r is theta. Let's find this angle first of all. This is going to be tan inverse of 12 over 5. So this is 1.176. So theta is 2 pi minus 1.176. 2 pi being 360. So it's 5.01 radians. So our polar coordinates are 13 and 5.11 radians. Okay, in the final one, we are going to go into the third quadrant because both coordinates are negative. So we're going to go somewhere here. I want to find this angle, find out what this angle is as my theta. So this is √3 and this is 1. There you go. So I'm going to just find this angle and add it to pi when giving the theta. So value of r is √3 squared, add 1 squared, square rooted, so it's 2, and the angle arc tan 1 over √3, which is pi over 6. So if this angle here is pi over 6, theta must be pi plus pi over 6. So that's 7 pi over 6. So our angle, our point has polar coordinates given by 2 and 7 pi over 6. So that's example 1 done. We've got 3 more to go before you can have a go at exercise, the first exercise. Okay, example 2. So this time, this is a lot quicker. You don't need to draw it actually. We're just going to use the formula for our r and for some formula for x and y, which I have not put here. Kind of stop there. Okay, so this is actually very useful. So y over r is going to be equal to sine theta. So y is r sine theta. X over r is cos theta, so x is r cos theta. These are also really important whenever you work with these coordinates. Okay, so let's have a go at it again. So like I said before, we need to use the definitions. X equals to r cos theta and y equals to r sine theta. So just a quick reminder, I wrote here a complex number, r cos theta plus r sine theta. Normally we have r outside, but when you multiply it out, that's what happens. Okay, so your r cos theta corresponds to the real part, which is along the x-axis, and r sine theta to imaginary part, which is along the y-axis. So your x and y coordinates. So here exactly the same needs to be done. We're just going to substitute 10, and you get a as r and theta as 4 pi over 3. So we are talking about being in the third quadrant, so it's going to be 10 times minus a half, which is minus 5. And here we've got 10 sine 4 pi over 3. Again, that's going to be negative minus √3 over 2. So it's minus 5 √3. Hence, minus 5 √3 are the two coordinates. Over here in part B, we are going to go through x is r cos theta, which is 8 cos 2 pi over 3. And that's going to be negative half, and y is r sine theta, so it's a sine 2 pi over 3, so sine is positive. It's minus 4 and 4 root 3 are the coordinates of the second point. Okay, so we can now go on to example 3. So this time the idea of describing curves in terms of their equations. In Cartesian form you have to have x's and y's. In polar form you've got to have r's and thetas in the equation. So for example, you've got r is equal to cos theta, that's an example of an equation. R is sine 2 theta plus 1, r is 5, that is an equation in polar form. Each of those equations can be converted into its Cartesian equivalent. So one of the skills is to actually change these given equations into Cartesian ones. So here's the first one, r is equal to 5. What you might find useful whenever you do questions like this is to write down that r squared is equal to x squared plus y squared, and also that your y is equal to r sine theta and x is r cos theta. Here you go. So first of all, you've got r is equal to 5. You can just use this. X squared plus y squared is going to equal to 5 squared. So x squared plus y squared is equal to 25. So this is circle centered at 0, 0, radius 5. This one here, I've lost an r. There was an r here. Apologies. So r is equal to 2 plus cos 2 theta. So which of these can we use? Well, at the moment, we could use, instead of r, you can just do x squared plus y squared square rooted. And then you've got cos 2 theta. So what can you do in terms of cos 2 theta? Well, the 2 theta is not really helpful. So what you want to do is get rid of 2 theta. So the way to do it is to use the identity for cos 2 theta. So you can either use cos 2 theta is equal to 2 cos theta plus minus 1, or you could use 1 minus 2 sine squared theta. Forgot the squared. There you go. Okay, so either of these two will suffice. So let's say we go for the first one, to replace the cos 2 theta with 2 cos squared theta minus 1. So it's 1 plus 2 cos squared theta is equal to r. Now that's still not very helpful, so one way of doing it is just replace your cos with x over r. There you go. Multiply everything by the denominator, which will be r squared, to get r squared. And then we're going to have plus 2 x squared is equal to r cubed. Okay, so over here, let's just, it's not a very nice equation at all. Let's do r squared, and then here we're going to do r minus 1. Okay, that doesn't actually help us much, so what we can just do straight away from this form, start substituting our x squared plus y squared. So let's do x squared plus y squared plus 2x squared is equal. Now this one here can be thought of as, if you think about it, to the power of 3 is the same as r squared raised to the power of 3 over 2. the 2's can cancel to give you 3. So r squared could be then replaced with x squared plus y squared, and then raised to the power 3 over 2. Like I said, it's not very nice. So you've got 3x squared plus y squared is equal to x squared add y squared to the power 3 over 2. I can't really make it look better than that. Okay, so this one over here, r squared can directly be replaced with x squared plus y squared, but sine 2 theta, that is definitely 2 sine theta cos theta. So you've got r squared is equal, now sine theta, you could replace it with y over r, and then cos theta with x over r. So you've got r, let's times it by r squared. So you've got r squared times r squared is equal to 2xy. So here you've got x squared plus y squared all squared is equal to 2xy. Again, I don't think this was quite nice in this form. If you start expanding it, it will look different, but you won't really be able to make either x or y the subject. Okay, so that's example 3. So obviously if you go from polar coordinates to the Cartesian coordinates, you need to also be able to do it the other way around. It's a little bit easier. So again, straight away, if we want to change these into polar coordinates, let's write the definition. So r squared is x squared plus y squared. Your x is r cos theta and y is r sine theta. Okay, so we're just going to replace those with x's and y's. So you've got r sine theta all squared is equal to 4r cos theta. So r squared sine squared and then 4r cos theta. Can divide by r to get r sine squared theta is equal to 4 cos theta. So r is equal to 4 cos theta over sine squared theta. Very often in those equations they might want to change it into cot and cosec, so that's what I'm going to do. It's 4 times cos theta over sine theta times 1 over sine theta. Okay, we got interrupted, so I'm not sure at which point. Just confirm it. At the end, we've converted, split this into cos theta over sine theta times 1 over sine theta, and then replaced cos theta over sine theta with cot and 1 over sine with cosec theta. Okay, the second example, x directly becomes r cos theta all squared minus r sine theta all squared is equal to 5. So you get r squared cos squared theta, if you factorize it, minus sine squared theta is equal to 5. That can be replaced with cos 2 theta, and then you've got r squared is equal to 5 over cos 2 theta, which is sec 2 theta. And you can leave your r as r squared. That's perfectly okay to do so. Okay, so this straight line over here, y can be r sine theta times root 3, and then you've got r cos theta plus 4. So r sine theta times root 3 minus cos theta, factorize the r, is equal to 4. Over here, it's nice to join it into one expression, so do a little bit of work on joining it together. Let me just write it as root 3 sine theta minus cos theta. So we're going to replace it with, let's say, r sine theta, there's a minus here, so minus alpha. So if you do that, then you've got r sine theta cos alpha minus r cos theta sine alpha. So you've got r cos alpha is equal to root 3 and r sine alpha is equal to 1. You've got root 3 squared, add 1 squared is equal to r squared, so r is equal to 2. So sine, let's do sine over cos, which is tan. Alpha is 1 over root 3, which is pi over 6 for alpha. So the replacement is going to be 2 sine theta minus pi over 6. Okay, so you've got r times 2 sine theta minus pi over 6 is equal to 4. So r is equal to 2 over sine theta minus pi over 6, which is 2 cosec theta minus pi over 6. There you go. So at the moment, this was example 5. You are ready to move on to exercise 5a.